Imagine standing on a rust-red shore as the Martian dusk paints the sky in hues of crimson and gold. Gentle waves lap at your feet, their rhythm steady and ancient, stretching toward a horizon where the dark water meets the fading light. Above, two moons, Phobos and Deimos, hover in the twilight, their jagged silhouettes a stark reminder that this isn't Earth. It's Mars, 3.6 billion years ago. A world that might have rivaled our own, with vast oceans teeming with possibility. But was this vision ever real? Could the red planet, now a frozen desert, have once cradled seas that nurtured life? Recent discoveries have reignited this question, pulling us closer to answers that could reshape our understanding of Mars and our place in the cosmos. Buckle up, because we're diving into a story of cosmic exploration, groundbreaking science, and the relentless human quest to uncover the secrets of our planetary neighbor. For decades, the idea of oceans on Mars has captivated scientists and dreamers alike. The notion isn't new. It's been whispered in research papers and debated in lecture halls since the 1970s, when NASA's Viking missions beamed back images of what looked like ancient riverbeds and floodplains. These tantalizing hints suggested a wetter, warmer Mars, a planet that might have mirrored Earth in its youth, but the evidence was always indirect, pieced together from satellite images, meteorite fragments, and climate models that didn't quite add up. Some researchers championed the ocean hypothesis, pointing to features like eroded valleys and sediment deposits. Others dismissed them as illusions, artifacts of low-resolution images, or the wishful thinking of scientists eager to find life beyond Earth. The debate raged on, fueled by a frustrating lack of direct evidence. Mars, it seemed, was a planet of contradictions. Polar ice caps the size of entire countries, dry river channels carved into its surface, yet no clear proof of standing bodies of water. Could there have been oceans, or were we projecting Earth's story onto a world that never knew such abundance? The answer remained elusive until a small rover from the China National Space Administration changed everything. On July 23, 2020, a spacecraft named Tianwen-1, meaning questions to heaven, launched from Earth carrying China's ambitions and a rover called Zhurong. Its mission was bold, to probe the mysteries of Mars's geology, climate, and potential for life. After a 202-day journey across 225 million kilometers, Tianwen-1 entered Martian orbit on February 10, 2021. 3 months later, on May 14, the lander touched down in Utopia Planitia, a vast basin in Mars's northern hemisphere. A week after that, Zhurong rolled onto the red soil, making China only the second nation to successfully deploy a rover on Mars. Utopia Planitia wasn't chosen by chance. This enormous impact basin, stretching 3,300 kilometers across, is one of the largest in the solar system. It's also a place of intrigue, suspected by scientists to be the remnant of an ancient ocean floor. In 2016, NASA's Mars Reconnaissance Orbiter detected a massive reservoir of underground ice in the region, enough water to fill Lake Superior, roughly 12,100 cubic kilometers. If Mars ever had oceans, Utopia Planitia was a prime candidate for their resting place. Zhurong, equipped with 13 scientific instruments, was sent to test this hypothesis, scanning the subsurface, analyzing rocks, and monitoring the Martian climate. What Zhurong found was nothing short of revolutionary. Using its ground-penetrating radar, the rover sent radio waves deep into the Martian soil, probing up to 100 meters below the surface. The signals bounced back, revealing a series of geological reflectors, layers of sediment that marked boundaries between different materials. But it wasn't just the presence of these layers that stunned researchers. It was their structure. All 76 reflectors sloped in the same direction, at angles between 6 and 20 degrees, forming a 1.3 kilometer stretch of terrain that tilted toward the lowlands. This wasn't random. It was a pattern, one eerily similar to the buried beaches of Earth's Bay of Bengal. The implications were staggering. These sloping layers, preserved 10 to 35 meters beneath the surface, bore the hallmarks of a foreshore, the dynamic zone between high and low tides where waves and sediment interact. On Earth, foreshores are shaped by the relentless push and pull of water, wind, and gravity, creating gentle slopes that record the balance of these forces over millennia. Zhurong's data suggested that Mars, too, once had such a place, a shoreline where waves lapped, tides rose, and sediment settled. It's a simple structure, but it tells you there had to be waves. One of the study's co-authors remarked, there had to be a nearby river supplying sediment, and all these things had to be active for some extended period of time. To ensure they weren't chasing a mirage, the team considered alternative explanations. Could these slopes be sand dunes or lava flows? Unlikely. Such features would produce slopes pointing in multiple directions, not the uniform tilt Zhurong observed. The evidence pointed to one conclusion: Mars once had a dynamic coastal environment, complete with tides influenced by the gravitational tug of its sun and moon, Phobos. For the first time, we had on-the-ground data supporting the existence of an ancient Martian ocean. Why does this discovery matter? To understand that, we need to talk about water. Not just any water, but the kind that pools into lakes, seas, or oceans. Water is the elixir of life as we know it. On Earth, it covers 70% of the surface and makes up 60% of our bodies. It flows through rivers, fills lakes, and drives the chemistry that sparked life billions of years ago. But in the solar system, liquid water is a rare commodity. Mars, despite its barren appearance today, shows signs of a wetter past. Crystals in Martian meteorites, dating back 4.45 billion years, suggest the presence of hot, water-rich fluids. Minerals like ferrihydrite, found in Martian dust, form only in water's embrace. And then there's the ice, vast deposits in the polar caps and beneath the surface, hinting at a world that once held more. But rivers and ice aren't enough to tell the full story. Rivers are dynamic, constantly flushing materials downstream, making it hard for the delicate chemical reactions needed for life to take root. Oceans, on the other hand, are different. Their shorelines are natural laboratories, concentrating organic molecules through evaporation, fostering the formation of complex molecules like RNA and proteins, and providing energy sources like ultraviolet radiation, heat, and chemical gradients. These conditions are ideal for the chemistry of life to emerge. If Mars had oceans, their shores could have been cradles for microbial life, leaving behind biosignatures, clues like fossilized microbes or organic compounds that we might still find today. Zhurong's discovery of a potential shoreline in Utopia Planitia is a game changer. It's not just evidence of water, it's evidence of a stable, standing body of water that could have supported life for millions of years. These ancient coasts might have hosted entire ecosystems, their remnants buried in the sediment waiting for us to uncover them. The rover's findings have given scientists a new target in the search for extraterrestrial life, narrowing the hunt to regions where the conditions for life were once perfect. But there's a catch, a puzzle that has baffled scientists for decades. Known as the faint young sun paradox, it challenges our understanding of how Mars could have sustained liquid water. 3.5 billion years ago, the sun was 25% dimmer than it is today, too weak to keep Mars above freezing. Yet the geological record, rivers, lakes, and now potentially oceans, suggests a warm, wet Mars. How could this be? Scientists have proposed 3 theories to solve this paradox. The first imagines a warm, wet Mars blanketed by a thick atmosphere rich in greenhouse gases like carbon dioxide and water vapor. This dense atmosphere could have trapped enough heat to maintain liquid water for millions of years, supporting rainfall, lakes, and oceans. But there's a problem. Our models show that carbon dioxide and water vapor alone can't generate the necessary warmth. Other gases like methane or ammonia might have helped, but they're unstable and unlikely to persist long enough. The second theory suggests Mars was only warm and wet intermittently, spurred by cataclysmic events like volcanic eruptions or asteroid impacts. These could have released bursts of heat or greenhouse gases, creating temporary warm periods where ice melted and rivers flowed. But were these events frequent or intense enough to carve the vast valleys and basins we see today? The evidence is inconclusive. The third theory paints Mars as a frozen world dominated by snow and ice, with occasional melting triggered by changes in its orbit or sudden heating events. This could explain the mix of glacial and fluvial features on Mars's surface, but it struggles to account for the scale of erosion and sediment deposition we observe. None of these scenarios fully resolve the paradox. Zhurong's shoreline evidence strengthens the case for a wet Mars, but it also deepens the mystery. If oceans existed, what kept them liquid? Was it a unique atmospheric chemistry, geological activity, or something we haven't yet considered? Solving this puzzle could unlock the secrets of Mars's habitability and perhaps even Earth's future. The sloping sediments uncovered by Zhurong are more than geological curiosities. They are echoes of a lost world, whispering tales of a Mars that once danced with water and wind. Picture a Martian coastline 3.6 billion years ago, where waves crashed against rocky outcrops, carving out beaches of fine sand and coarse pebbles. Rivers, fed by distant rains or melting glaciers, poured into these ancient seas, carrying sediments that settled into layers, each one a snapshot of a moment in time. These layers, now buried beneath the Martian surface, are like pages in a book, preserving the story of a planet that may have been alive with possibility. The uniformity of the slopes, tilting consistently toward the lowlands, suggests a stable, long-lived environment where water didn't just flow but lingered, shaping the landscape over millions of years. This wasn't a fleeting flood or a temporary lake. It was a dynamic system with tides influenced by Phobos and Deimos, and perhaps even storms that churned the waters and reshaped the shores. These sediments could hold the key to finding biosignatures, organic molecules, or fossilized microbes that would confirm whether life ever took root on the red planet. As we stand on the brink of this revelation, the question isn't just whether Mars had oceans, but what those oceans might have nurtured in their depths. The story of Mars's oceans is also a story of human curiosity, a testament to our unyielding desire to understand the universe. From the grainy images of the Viking missions to the sophisticated radar of Jurong, each step in our exploration of Mars has been a leap toward answering one of humanity's oldest questions. Are we alone? The discovery of a potential shoreline is a milestone in this quest, but it's also a reminder of how much we still don't know. What caused Mars to lose its water and atmosphere? Did life emerge in those ancient seas, only to vanish as the planet grew cold and dry? Or could microbial life still persist, hidden in subsurface aquifers or frozen in the polar ice? These questions drive scientists to push the boundaries of technology, sending rovers to distant worlds and planning missions to bring Martian soil back to Earth. But they also inspire us all, students, dreamers, and explorers, to look up at the night sky and wonder. The search for Martian oceans isn't just about science, it's about our shared longing to connect with something greater, to find our place in the vast tapestry of the cosmos. As we uncover more about Mars's past, we're also learning about our own planet's future, grappling with the fragility of the conditions that make life possible. The red planet, once a mirror of Earth's youth, now stands as a cautionary tale and a beacon of hope, urging us to protect our world while we reach for the stars. As we reflect on Jurong's findings, we're left with a sense of awe and anticipation. The evidence for Martian oceans opens a new chapter in our exploration, but it also raises the stakes for what comes next. If Mars once had stable seas, what happened to them? Scientists theorize that the planet's thin atmosphere and weak magnetic field allowed its water to escape into space or freeze beneath the surface. Some estimates suggest that Mars lost 99% of its surface water over billions of years, leaving behind the dry, dusty world we see today. Yet the possibility of underground reservoirs, perhaps even pockets of liquid water, keeps hope alive for finding traces of ancient life. Future missions will target these regions, using advanced drills and spectrometers to probe deeper than ever before. China's plans for a sample return mission by 2033, and potentially a crewed mission in the decades that follow, signal a new era of exploration. Meanwhile, international collaborations are exploring ways to overcome the challenges of Mars's harsh environment, from radiation to dust storms, to ensure that future rovers and astronauts can continue this work. The dream of standing on a Martian shore, sifting through its sediments for signs of life, is closer than ever. But this journey isn't just about Mars. It's about humanity's future in space, about the technologies and discoveries that could one day take us to other planets, moons, and even distant stars. The story of Mars's oceans is a reminder that every answer we find is a stepping stone to the next great question, pushing us to explore further, dream bigger, and never stop asking what lies beyond the horizon. To fully grasp the significance of Mars's ancient oceans, we must delve into the planet's climatic evolution, a saga of transformation that turned a potentially vibrant world into the desolate landscape we see today. Billions of years ago, Mars likely boasted a thicker atmosphere, rich with gases that could trap heat and sustain liquid water. Evidence from meteorites and surface minerals suggests that early Mars experienced cycles of rain, snow, and perhaps even seasonal changes, not unlike Earth's. The presence of vast river valleys, such as Valles Marineris, and outflow channels like those in Crisi Planitia, points to a time when water flowed freely, carving deep scars into the planet's crust. But something changed. As Mars's magnetic magnetic field weakened, its atmosphere began to erode under the relentless bombardment of solar wind. Without this protective shield, water vapor escaped into space, and the planet cooled, locking much of its remaining water into polar ice caps and subsurface reservoirs. Zhurong's discovery of a shoreline in Utopia Planitia adds a new layer to this story, suggesting that oceans persisted long enough to shape the landscape in ways that only stable, standing bodies of water could. These ancient seas may have been fed by a combination of rainfall, glacial melt, and geothermal springs, creating a complex hydrological cycle that supported diverse environments. Understanding this transformation isn't just about reconstructing Mars's past, it's about learning how planets lose their habitability, a lesson that resonates as we face climate challenges on Earth. The Martian climate, once dynamic and life-friendly, now serves as a stark reminder of how fragile planetary ecosystems can be, urging us to protect our own while we search for clues to Mars's lost worlds. The possibility of Martian oceans ignites one of the most thrilling prospects in science: the search for biosignatures, the chemical or physical traces of ancient life. If Mars's shores were once cradles for microbial ecosystems, they could hold clues like organic molecules, isotopic anomalies, or even microscopic fossils preserved in the sediment. Zhurong's radar data points to Utopia Planitia as a prime target for this hunt, where layered deposits might encase the remnants of life that thrived billions of years ago. On Earth, similar environments, like the stromatolite-rich coasts of ancient Australia, preserve evidence of early microbes, offering a blueprint for what we might find on Mars. The challenge lies in distinguishing true biosignatures from abiotic chemical processes, a task that requires sophisticated instruments and, ideally, samples returned to Earth for analysis. Future missions, like China's planned sample return or NASA's delayed Mars sample return, will focus on collecting rocks and soil from regions like Utopia Planitia, where Zhurong's findings suggest the best chance of uncovering life's fingerprints. But the search isn't just about finding life, it's about understanding the conditions that allow it to arise. Mars's ancient shores, with their mix of water, minerals, and energy, could reveal whether life is a cosmic fluke unique to Earth or a universal phenomenon waiting to be discovered. This quest pushes the boundaries of science, blending chemistry, geology, and astrobiology in a pursuit that could redefine our understanding of the universe and our place within it. The discovery of a potential Martian shoreline is a triumph not just for China, but for the global scientific community, highlighting the collaborative spirit that drives space exploration. While Zhurong's mission marked a milestone for China's space program, it builds on decades of work by NASA, the European Space Agency, and other international partners. The Viking missions of the 1970s, NASA's rovers like Curiosity and Perseverance, and orbiters like the Mars Reconnaissance Orbiter have all contributed to our understanding of Mars's watery past. Zhurong's data complements these efforts, adding ground-based evidence to a mosaic of satellite imagery, atmospheric studies, and geological analyses. As we move forward, international cooperation will be key to overcoming the challenges of Mars exploration. The high costs, technical complexities, and environmental hazards, like dust storms and radiation, require shared expertise and resources. Initiatives like the Artemis Accords, signed by multiple nations as of September 25, 2025, aim to foster collaboration in space exploration, including future Mars missions. China's plans for a sample return by 2033, alongside potential contributions from Europe, Japan, and others, could accelerate our understanding of Mars's oceans and their implications for life. This global effort isn't just about science, it's about humanity uniting to answer fundamental questions about our origins and our future. As we stand on the cusp of new discoveries, the story of Mars's oceans reminds us that exploration is a shared journey, one that transcends borders and inspires generations to look to the stars. The story of Mars's potential oceans is not just a tale of a distant world, it's a mirror reflecting our own planet's past, present, and future. Mars, in its youth, may have been a twin to early Earth, with flowing rivers, vast seas, and an atmosphere thick enough to cradle life. Yet, over billions of years, it underwent a dramatic transformation, losing its water and air to become the cold, barren desert we see today. This cosmic cautionary tale forces us to confront the fragility of planetary habitability. On On Earth, we take for granted the delicate balance of atmospheric gases, magnetic fields, and liquid water that sustain life. But Mars shows us how quickly that balance can tip. The same processes that stripped Mars of its oceans, solar wind, atmospheric loss, and climatic shifts could, in the distant future, threaten Earth if we fail to steward our planet's resources. Zhurong's findings, by illuminating Mars's watery past, underscore the urgency of addressing climate change and environmental degradation here at home. They also inspire hope, showing that even a planet as seemingly inhospitable as Mars might once have harbored life, suggesting that the conditions for life are more resilient than we thought. As we probe Mars's ancient shores, we're not just searching for alien life, but learning how to protect our own, ensuring that Earth doesn't follow the same path as its red neighbor. This dual perspective, looking outward to Mars and inward to Earth, fuels a sense of responsibility and wonder, urging us to act as caretakers of our planet while we chase the mysteries of the cosmos. Behind Zhurong's groundbreaking discovery lies a marvel of human ingenuity, a testament to the technological leaps that have made Mars exploration possible. The rover's suite of 13 scientific instruments, from ground-penetrating radar to laser-induced breakdown spectrometers, represents the pinnacle of engineering, designed to withstand the harsh Martian environment while collecting precise data. The radar in particular was a game-changer, capable of peering up to 100 meters beneath the surface to map subsurface structures with unprecedented clarity. This technology, honed through decades of innovation, allowed scientists to detect the subtle signatures of ancient shorelines, transforming abstract theories into tangible evidence. But Zhurong's success wasn't just about the rover itself, it was about the global infrastructure that supported it. From the Tianwen 1 orbiter relaying data across millions of kilometers to the ground stations decoding signals on Earth, the mission required a symphony of coordination, computing power, and expertise. As of September 25th, 2025, advancements in AI and data analysis continue to enhance our ability to interpret Martian data, with machine learning algorithms helping to identify patterns in Zhurong's radar images that might have been missed by human eyes. These technological triumphs are not just tools for exploring Mars, they're stepping stones to a future where humanity might one day walk on the red planet, build habitats, and perhaps even revive its ancient waters. The story of Mars's oceans is as much about the machines we build as the discoveries they enable, a reminder that our reach into the stars is powered by the relentless creativity of the human mind. Zhurong's mission, though brief, was a triumph. Designed to operate for 93 Earth days, the rover soldiered on for 358, collecting data until May 20th, 2022, when dust accumulation sent it into dormancy. Scientists hoped it would awaken in December 2022 with better sunlight, but it never did. Yet its legacy endures, offering the strongest evidence yet for Martian oceans and setting the stage for future exploration. But the story doesn't end here. If Mars had oceans, what happened to them? Did they evaporate into space as the planet's atmosphere thinned, or are they locked away in underground reservoirs? Could traces of ancient life still linger in the sediment, waiting to be discovered? And what does Mars's transformation from a potentially habitable world to a barren desert tell us about the fate of planets, including our own? To answer these questions, we need more data. NASA had planned a Mars sample return mission for the late 2020s, with samples arriving back on Earth in the early 2030s, but budget uncertainty have delayed this to 2040, and recent proposed cuts threaten to cancel it entirely. China, meanwhile, is planning its own sample return mission, possibly by 2033, and even a crewed mission to Mars in the coming decades. These efforts could provide the physical evidence, rocks, soil, and perhaps biosignatures needed to confirm Zhurong's findings and settle the ocean debate once and for all. The discovery of a potential Martian shoreline is more than a scientific milestone. It's a call to action. It reminds us that the universe is full of mysteries waiting to be explored, and each answer we uncover raises new questions. Did Mars once host life? Could it again? And what does its story teach us about preserving the fragile conditions that sustain life on Earth? As you ponder these questions, let's keep the conversation going. Share your thoughts in the comments. Do you think Mars had oceans? And what might we find if we dig deeper? Hit that like button if this journey to the red planet sparked your curiosity, and subscribe for more stories that take you to the edges of human knowledge. Together, let's keep exploring, questioning, and dreaming of the day we might stand on a Martian shore, looking out at a sea that no longer exists, but whose secrets still whisper to us across the ages.